Hi, welcome back. In this video and videos to follow, I'm going to solve simple harmonic motion problems that come right out of your book. The first three problems are all going to deal with springs and spring systems. So I'll show you how to analyze them, how to think about them, and highlight what equations to use when you do that. Okay, so in this one we have a fisherman's scale. So this is kind of like one of those scales you have at the grocery store. They're kind of being replaced by digital ones, but the ones that pull down. So we have a scale. Let's go ahead and annotate this. Oopsie. So we have a fisherman's scale that stretches that far when we put a fish on it. So condition 1, we have this. So I'm just going to make a dotted line. And we know that this will stretch a little bit when we put the fish on it, right? So here's my glorious, beautiful fish. Yep, so that's pretty. And we know that it stretches 0.036 meters. So notice that I just went automatically into meters instead of centimeters here. So A, what is the stiffness constant of this? So this is part A. So we have the mass of the fish. So if you think about the forces that are acting on this fish, we have the weight of the fish, mg, and then the spring is going to counteract this weight, right? So it's going to go in the opposite direction. So what we could say is we could say that the force spring is equal to mg. And the reason why we could do that is because we can see that this is at rest right now. We're in equilibrium. So kx equals mg. And then we're looking for the k constant. So k is going to equal to mg over x. So k will be mass times g over x. So let's go ahead and calculate that. So the answer is 735.8. And the spring constant is measured in newtons per meter, like that. So that's part A. Part B, now it says we start to oscillate it, right? So it's going to have an amplitude of that. And the question is, well, I already answered that question, but what's the frequency? So let's go ahead and just rediagram this out. So now what we're going to do is we have the fish. And then what we're going to do is we're going to set that fish into motion. So notice we're going to draw a new line for that. It's 0.025 meters. So once again, I'm going to convert that centimeters into meters. So for amplitude, this represents the amplitude. Is how much we stretch it, just like that. So A is the 0.225, so that's the easy part. Just look at that number. And yes, you could write it in centimeters in this part because it doesn't specify, but I like to just keep things in meters. But now we need to know the frequency. So what we could do is we can calculate the period, 2 pi root m over k. And what we can do is, once we find that, we could take the inverse of it to get the frequency. Just like that. So period is 2 pi square root of the mass divided by the 735, so the k constant that we got earlier, 0.8 newtons per meter. So let's go ahead and do that. So 0.38 seconds. And then to get the frequency, I'm just going to take the inverse of that number. So it becomes 2.62 hertz. So there you have it. That is the frequency of the system. Let's try this one. Let's move this up. So now we have a object of that mass attached to a spring with the constant that is executing simple harmonic motion. When the object is that many from its equilibrium, it's moving with that speed. Calculate the amplitude, calculate the maximum speed. So in this problem, they tell us that we have a position in speed, so this is not a maximum or minimum condition. So this is somewhere in the middle. So basically, if I were to diagram this, so this is the equilibrium position, this is the max position, the information they gave us was somewhere in the middle right here. So what we have is velocity at this point is 0.55 meters per second, and we're stretched 0.02 meters from here to here. Question is, what is the amplitude and what is the velocity max? So the best way to solve this problem is to use conservation of energy. So we know that the total energy can be represented by the maximum positions at any point. And then we could set that equal to the total energy at that moment. So for example, if I want to find the amplitude, I could do 1/2 kA squared, which represents the amplitude here, the maximum from here to here. That's A. Not drawing the scale, sorry about that. Then we're going to say 1/2, so at that middle position, it's going to have the following information. Because we know all the energy will be put into potential at this point, and all the energy will be put into kinetic at this point, so some in the middle is going to have a combination of the two. So because, there you go, because they're all the same values between each of them, we can actually simplify this. And there we go right here. So then what we could do is we could actually plug in our values that we have, because we have all of these features. So I moved it up. Sorry. 280. And then we have, let's see, I'm just going to circle the information. So 280 was our K, so 280 goes here. And then the mass, let's go ahead and plug that in, is 3. So the velocity there, I'm just getting all the information as you can see. And then K. And then the position at that point is 0.2 meters squared, like that. So that's the setup. So I'm going to go ahead and just do the algebra and get to a squared. So it's going to take me a second to do this, but let's go ahead. So I'm going to do 3 times 0.55 squared plus 280 times 0.02 squared. Oops. Okay. Then I'm going to divide by 280. And then I have to square root that answer. 0.06. So I just solved for A. I just jumped the gun here. And I'm just going to run through that calculation again, because I think I may have made a mistake, but that's the idea. But I'm pretty sure that's okay, so let's just do it really good. So 3 times 0.55 squared plus 280 times 0.02 squared gives me that, divided by 280, square root of the answer. Yes, I got the same answer. I was just double checking. Okay. So that's how you can solve that out. So we know the maximum amplitude, and this makes sense because we know that the previous amplitude was 0.2, so the amplitude should be larger, the maximum amplitude. So that looks good. So that's part 1. Part 2 says, what's the maximum velocity? I like to solve it this way. So I say that all the kinetic energy goes into the velocity. Where actually, let me rewrite this, I'm going to use A, the thing that we just calculated, to find the max velocity. These cancel, and what we get is K A squared over M. It's going to give us our maximum velocity squared, of course. So let's go ahead and do that. So A squared times 280 divided by 3, square root of the answer. The max is 0.583 meters per second, just like that. Okay, so that's the maximum energy, maximum velocity at that point. Okay, so in this problem, we're looking for the period of the spring. So they gave us all the information, so the one that I like to use is the spring period equation. M over K, just like that. So the period of the spring is going to be 2 pi square root of the mass, 0.5, divided by 50, like that. So let's go ahead and do 0.5 divided by 50, square root of the answer, times 2 times pi. So our period here becomes 0.628 seconds. So this one was a nice one. It was pretty straightforward because they gave us all the information to solve for the period of the spring. So the question is, what is the maximum speed if we have this amplitude and that frequency? So for this problem, it's good for the AP students to know that you could actually calculate this using a different equation. So if we treat the motion of an object that's oscillating like a circle, we'll find that the amplitude is the radius and t is the frequency. T is the period. We could also write it like this, because t, 1 inverse t is technically f, so I can write it like this. So this again comes from the idea that we could treat it like an object moving in a circle. So this is the fastest and best way to calculate this. 2 times our amplitude times our frequency. So 2 times pi times 0.02 times 60. So the velocity is this. So I literally just kind of threw this out there out of nowhere. But like I said, where that comes from is if we treat, in the previous, the first video, we saw that an object that oscillates up and down like this will actually trace out a circle, right? If we were to model it. So A represents this. T represents how long it takes to make that circle. And notice if we were going to look in this phase space, it would be 2 pi a for the distance, and then of course the velocity has to have a timing feature, and that's the time it takes to go around. So that's where this kind of came up in terms of the equation right here. So this can work for oscillations, which is very helpful too. Okay, so you know what? I'm going to leave this one just to see if you can solve it on your own, but we're using more or less the kind of the concepts that we talked about earlier when we were solving all of this. The frequency, the maximum speed, acceleration, and then the total energy of the system. I have the answers in the slides, so you could try them out, or if you have any questions, you could either email me or let me know in advance. But this will conclude our slideshow on how to calculate simple harmonic motion using springs.